Okay, so for our next problem is in our example number 4. So in our example number 1, 2, and 3 is we are dealing with inductance and resistance connected in parallel. But this time, in our fourth example is we are now dealing with capacitor connected in resistor parallel. They are connected in parallel. Now, uh, in this problem is and our impedance for the capacitive circuit, or it has capacitive, only dealing with resistance and capacitor, is that this is R plus, no, it is minus X sub C J, and then the total current is, this is also equal to I sub R minus I sub C J, and of course the power is S is equals to 2 power minus QJ. Okay, so that is the it is the rectangular form for our impedance, total current, and then the apparent power. Okay, so first again is we must create a circuit diagram to visualize the actual circuit. So our first impedance, and that is our second impedance. So our first impedance is Z sub 1, our Z sub 2. So this is our E. So the current that flows here, this is I. And it after this node, this is our I sub R. And here is our I sub C. Okay, so in the problem, so since the capacitor value and then the resistor value is given, so I think we could apply the shortcut method, or the same process with example number 1 and number 2. So first we're going to solve for the total impedance. So we know that our first impedance, C sub 1, is a pure resistive. Let's say this is our 80 ohms. And our second impedance, this is our pure capacitive, which is 30 microfarad. Is we will convert that into its capacitive reactance. So the our x sub c is, this is 1 over 2 pi. Our frequency given is 50 hertz. And then our capacitor is 30 times 10 raised to negative 6. So with this is equals to 1 over 2 pi times 50 times 30 times 10 raised to negative 6. Okay, so 106.10. 106.10. So our X sub C is 106.10 ohms. So this is our Z sub 2, which is negative 106.10 J. Okay, so this is only applicable for pure capacitive branch. Okay, so getting the total impedance for our circuit, our Z is equals to 1 over 80 Z sub 1 plus 1 over negative 106.10 J. So with this, we could get the rectangular form for the total the total impedance in terms of rectangular form. Okay, so 1 over 80 plus 1 over negative 106.10 I. Okay, so we have a 51 minus 38.46. So this is 51 minus, okay, 51 minus 51, again, 51 minus 38.46. 38.46 J. Now, if our impedance, this will be converted into a polar form, just use your calculator, uh, complex mode conversion. So if you convert this, this is equals to 63.88 says of negative 37.017.01 degrees. Again, this is already our phase angle. Okay, next is we're going to solve for the total current. Our total current is equals to E over Z I. Our total supply voltage is equals to 240 volts. Our impedance is 63.88 angle of negative 37.01. Okay, so our current, using your calculator, our current is equals to 3 plus 2.26 J. And if you convert this into its polar form, this equals to a 3.76 angle of 37.01 degrees. And again, to get for the apparent power, this is equals to P EI, voltage times current, 240. Our total current is 3.76 angle of 37.01. So our apparent power is equals to let me see in my solution here. So you can use a calculator. That is equals to 720 plus 543.08 J. Okay, so now by inspection, so we know that in here, so this is our total impedance. This is our Z. Okay, so let's go back with our what is asked, the current in this problem. So 3 ampere is for our I sub R, the current that flows in our Z sub 1. 2.86 is for our I sub L. 3.76 is for our total current. 3.01 is for our phase angle. Now, 63.88 is the circuit impedance, and the same. And for the power is, we are also looking for the power in watts and the apparent power. So in our problem, if this rectangular form, if you convert this into its polar form, this is equals to 902.4 angle of 37.01 degrees. So this is our true power in watts. 543.08 is our reactive power in volt ampere reactive, or VAR. 902.4 is our apparent power in volt ampere, and still this is our phase angle. So if you observe, there are small discrepancy between our volt power, apparent power. So it's because of the sum of the decimal place that we use. It's because it's only two decimal places. So again, I suggest use at least four decimal places. So this is for our example number 4. Okay. In our fifth example is we are dealing again with a capacitor connected in parallel with a resistor. So now our big problem is, I think it's a more complicated in a way that it is a different type of example because it has no capacitance and it has no resistor value. So we are only having a voltage supply which is 120 volts, its power supply, and also we have also given the current that flows in the circuit and its power factor, which is 0.6. Now we are going to get the capacitance and the resistance value. Okay. So first is so after, since we already identified the givens, now we know already what is asked also, and then we must get the equation. So to solve for our resistance, so we know that the resistance formula, it is just related with its voltage, the voltage supply. It's because it's just equal with the voltage that voltage across the resistor over the our uh, I I sub R. So that is the value. Now, also for our capacitor, the capacitor is just related with the capacitive reactance, which is equals to 2 pi F times X sub C. Now, with this, we don't have an I sub R, we don't have an X sub C. So what is only available in here is the voltage supply, the total current. So first is, I think we could get, we will use the power factor. So we could get the phase angle of the circuit. So we know that the power factor is just equal to cosine theta equals to 0.6. So therefore, our cosine is equals to 0.6. Okay. So with that, we know that the using your calculator, the cosine, our cosine of 0.6 is equals to 53.13. This is equals to 53.13. Okay, so with this, we could say, okay, here, so our current, again, let us be guided that our impedance in capacitor and resistor in parallel, our impedance is equals to resistance minus the capacitor reactance J, or it is equals to Z, sorry, this should be plus, okay, sorry. So this minus, but this is also negative theta. Now, in terms of current, the total current is equals to I sub R. This is now plus I sub L. So it's a matter of different signs compared to the inductor and resistor connected in parallel, or RLA, parallel circuit. So just check the comparison of the two compared. So this is I, total current of leading. Again, we are using the current as a reference to know what would be the type of circuit if it is lagging or leading. Okay, so with this, since we have a 120 volts and we have also a 2 ampere I think we could get the impedance, the total impedance. So our total impedance is equals to our E over I, and now this is equals to 120 volts, and over our total current is, so our total current is given 2 ampere, and then so we could say that the polar form for our total current is this is equals to 2 sets of 53.13 because our phase angle is 13. So therefore, our I, so if we are going to convert this polar form into its rectangular form, this is equals to 1.2. So just use your calculator. So this is equals to 1.2 plus 1.6 J, this one. So and of course, we know that The first term that doesn't have in a J is our I sub R. This is our I sub R. And then this one is our I sub C. So sorry pala, so it should be I sub C. So this is I sub C. Okay. So now I think we can get the value of our resistance. Resistance. Resistance is equals to 200, 120 pala, 120 volts over 1.2. So our resistance is equals to 100 ohms. Okay, now, so this is our final answer. Now, our last problem is how to calculate our X sub C. Okay, so we know again that in the circuit, using the impedance Z sub 1, Z sub 2, our E. So our Z sub 1 is equals to R, and our Z sub 2 is equals to, this is X sub C, J, this is negative. This should be negative as an indication that it is a leading, or it is a capacitive reactance. Okay, so with this, uh, in our problem is our Z. So I think the Z now, so this is not yet, I think it is not applicable. So what would be the X sub C? X could get the, how to get the X sub C? Okay, so let me see. Okay, so to get the X sub C, X sub C, our X sub C is, uh-huh, okay. So we know that our Z sub 2 is equals to negative X sub C J. Okay, so how are we going to get for the X sub C? Okay, okay. So I have an idea. So I think to get the X sub C, to get the X sub C, so we must use the formula E over I sub C. Our X sub C, we know that our E is already given, which is 120, 120, and also our I sub C is given, which is 1.6. So with this, our X sub C is equals to, okay, 75 ohms. So let me 1 over 2 pi, 200. X sub C is 75. Okay, so our answer is 10.61. So, okay, so using this formula, so the same code. So our C now is equals to 1 over 2 pi 200 times 75. Our C is equals to 10.61 microfarad. So this is our answer. So thank you for listening. Okay. For our sixth example is we are having a capacitor connected in parallel with a resistor. So it's the same with our example, the previous example, but this problem is now, I think it is more easier. It's because we have a capacitor and resistor value. So we are using the shortcut method. So in the problem is we have 1500 nanofarad capacitor, and we have also 16 ohms resistor, and our given our given voltage supply or supply voltage is 10 volts and the supply frequency is 10 kilohertz or 10,000. So we are going to find for the current in each branch, supply current, circuit phase angle, impedance, the power consumed, apparent power, and circuit power factor. So let's start with given the, we will start with the circuit diagram. So in our circuit diagram, so we know that in our circuit diagram, this is only 10 volts. So I think it's a very small amount of power supply. Okay, so our first impedance, and then our second impedance is here. This is our Z sub 1, this is our Z sub 2. Okay, so now our Z sub 1 is this our capacitor let's take that this is our C sub 2. Our C sub 1 is our pure resistive branch. So this branch, let's say that it is a pure resistive. Okay, so this is a 16 ohm. Again, since it's pure resistive, and we are dealing with rectangular component. And Z sub 2 is, this is, since this is capacitor, it should be negative X sub C J, or X sub C, and as of now, we don't have the X sub C. So that is why we get first the X sub C by using the value of the capacitance, which is by formula, X sub C is equals to 1 over 2 pi. Our frequency is 10,000. And then our capacitor is 1,500. Nano is 1 times 10 raised to negative 9. Okay, so using your calculator, so we could get to solve 1 over 2 pi, 10,000 times 1,500 times 10 raised to negative 9. Negative 9. Okay, so therefore our X sub C is 10.61. X sub C, or the capacitive reactance, is 10.61 ohms. So therefore, our Z sub 2 here is 10.61 J. Again, this should be negative as an indication that it is a capacitive, or it is a pure capacitive. Now, our next goal is to solve for the, of course, the total impedance. So the total impedance is equals to 1 over 16 plus 1 over plus 1 over a negative 10.61 pi. So 4.89 minus 7.37. So 7.37 J. So again, sorry. So this should be 1 over negative 10.61 J. Okay. So our total impedance now is here. This is a rectangular form, and our next step is to convert this into a polar form. So we have 8.84 angle of, or SAS, sorry, a negative 56.45. So negative 56.45 degrees. Okay. So next step is we are going to solve for the total current. So in order for us to solve for the current for each branch. So our current is we know exactly, or basically, that it is equal to a voltage supply over the total impedance, which is what we have solved a while ago. So our current, so our total voltage is equals to 10 volts, and our total impedance is 8.84, or you can use also the rectangular form. They are just the same, negative 56.45 degrees. Therefore, our current is, let's check, plus 0.94 J. Okay, so, uh-huh. So let us convert this into its polar form. So we have 1.13, 1.13 of 56.45 degrees. So again, next is to solve for the total power. So the total apparent power is equals to E times I, or the voltage supply times the current. So this, our apparent power is our E is 10 volts only, and our current is given is, let's use the polar form, 1.13 angle of 56.45 degrees. So therefore, so current, let's multiply by 10. So we have our total power is 6.25. Our total power in a rectangular form is 6.25 plus 9.43. So plus 9.43 J. And also, if we are going to convert this into its polar form, the polar form. So we have 11.31 to 6.45 degrees. Now, as we observe here, exactly in our problem, what would be the current in each branch? So we know that using the rectangular form of the total current, we could get the, so the 0.063, this is now our I sub R, or the current that flows in the first impedance, or the pure resistive branch, or the resistor. 0.94 is for I sub L, and then 1.13 is what we are looking, this is already our total current or supply current, 1.13. This is our supply current, I. And then this is our 56.45 is our phase angle, which indicates that it is leading. And also here, 8.484 is the our impedance, total impedance, and the same also. This is our, and in terms of power, the 6.25 is our true power in watts, and 9.43 is the apparent reactive power in volt ampere reactive. Okay, so this is our true power, and this one is our apparent power. Sorry, reactive. This is our reactive power. Well, the 11.31, this is our total apparent power. Current power, and same again, this is our phase angle. Now, in the last what required is the circuit power factor, and basically again that the power factor is just equal to cosine theta, right? So therefore it is equal to cosine 56.45. So our power factor is now equal to cosine of 56.45, 0.55, 0.553. Okay, again, it's leading using the value for our current, the polar form. So it is the phase angle is plus, so it's leading. Okay, so that's all for our example number 6.